Good morning, everyone. I hope everyone's staying safe and staying healthy and staying in the house. Of course, I'm here at the school, moving right along. So we're going to go ahead and get into chapter 27. That's for my 135. Let me go ahead and pull that up. Okay, so chapter 37 is refrigerant leak testing. There we go. The objectives of this chapter are list issues to check for in a preliminary visual leak prevention inspection, explain the trigger rates that require mandatory leak repair, discuss inert gas leak detection techniques, list types of refrigerant leak detection, discuss proper refrigerant leak detection techniques, calculate the effect of ambient temperature change on a standing pressure test, discuss leak testing procedures for low pressure systems. So leak prevention, that is better than leak detection, it's leak prevention. Reduce refrigerant emissions through good service practices, leak detection, refrigerant recovery. Keeping the refrigerant inside of the system protects the environment. Leaking refrigerant systems are expensive. Obviously, you're wasting refrigerant and you have to pay for repairs, which could be pretty expensive. Expensive non-repairs. Customers may believe they are saving money by not paying for the expensive repairs. They're actually paying for repairs in the form of increased power bills. We talk about that all the time. The biggest thing is runtime. If your system is not at its peak or optimal potential, then it's going to take longer to do its job. Even if it is actually cooling, it's going to take longer to cool because it's not performing. And a leak is one of those things where, depending on the size of the leak, the system might still be cooling, but not as good as it would if it had all of this refrigerant. So prevention is key. Next step would obviously be leak detection and repair. So preventing problems, prevention. Always test the system for leaks before they are charged. It is good service practice to take steps toward recognizing and fixing potential problems, which is why we always pull our nitrogen out, charge up the system after we do whenever we open the system after we finish brazing, we always pressure test it with nitrogen, pull out the soap bubble, make sure we got, make sure we check for any leaks before we go charging the system back up. So preventing problems, inspection. When inspecting a system for leaks, take time to do a quick preliminary visual inspection. Make sure refrigerant lines and joints have been assembled properly and sufficiently braced, and supported. Signs of refrigerant leakage: oily area versus system superheat and subcooling. There are several signs of refrigerant leakage that technicians should recognize. Refrigerant oil travels with the refrigerant in the system. Over time, the area around the leak will appear oily and will attract dust and dirt. Systems operating with leaks will have a high system superheat or low system subcooling, a low capacity due to lack of refrigerant. The compressor will be hotter than normal because of the reduced amount of refrigerant. So those are clear indicators right there. Low superheat, high superheat, low subcool, could be leaks. There are other things that could make that happen that will make your system appear to be leaking when in fact it's something else, like a dirty filter or something like that. But those oil spots are also a dead giveaway. Trigger rates. Commercial and industrial process refrigeration trigger rate, required documentation, comfort cooling, and other rate. So the EPA only requires leak repairs on systems with a refrigerant charge of 50 pounds or more if leak meets EPA established trigger rates. The trigger rate for commercial and industrial process refrigeration is an annual leak rate of 35% of the total charge. Comfort cooling, which is, air conditioning, like residential, like commercial. Comfort cooling and other applications are restricted to an annual leak rate of 15% of the total charge. The work rate, the work rate includes the speed with which the refrigerant is lost. When technicians find a significant leak, they are required to inform owners in writing. The owner has the owner then has 30 days to repair the leak or submit a plan to the EPA to replace the system. System pressure. Check pressure. Most leak detection systems rely on detecting gas that is escaping from a leak. This assumes there is still something in the system to escape. The first step should be to check the pressure on the system. So you're gonna definitely want to hook your gauges up. If you suspect a leak, if the system's not cooling, and everything is turning, all your fans are turning, you know, contactors pulled in, it appears that everything's running normal, but you're not getting any cooling, or you know, you feel like there may be a leak. You want to go ahead and hook your gauges up first. That's going to be the dead giveaway. You hook your gauges up, you're not reading no pressure, or you're reading very little pressure, that's going to be a dead giveaway. Next thing you're going to want to do is move on to leak checking. So system pressure, check pressure. Most leak detection systems, okay, moving on. Unlisted system pressure. If a system doesn't list a test pressure, use 150 PSI as the maximum safe test pressure. So that's where I usually go to. At 150, you could pretty much exploit any leak. Some people like to go to 250, which is fine depending on the system. You just have to check the test rates. It's usually on the data tag. Leak testing with inert gas. Two methods of detection: soap bubbles, ultrasonic detectors. The soap bubble, that's the one. That's the one you're going to use all the time. Everything else you kind of use to get into the general area, then you pull out the soap bubble to really pinpoint the actual leak itself. So there are two methods of detecting refrigerant leaking from the system. One involves soap bubbles and the other ultrasonic detectors. Soap bubbles and nitrogen can locate the major or any major leaks in, in field fabrication. Escaping gas blows bubbles when the soapy solution is applied to the leaking area. Ultrasonic leak detectors check for leaks by listening for the high-pitched whistle the gas makes as it escapes through small holes. Safety with CO2 and nitrogen. So CO2 and nitrogen can be dangerous. They come in cylinders, pressure regulators, and pressure relief valves. Never use oxygen for pressure testing, ever, ever. So even though CO2 and nitrogen are inertly safe, both can be very dangerous because neither irritates the lungs or eyes. Um, there is little warning that there's little warning that the closed area a technician is in is full of nitrogen, that there is no longer enough oxygen to breathe. Nitrogen and CO2 cylinders can also be dangerous because of the very high pressure inside them. They typically have over 2,000 psi-G of pressure when the cylinder is new. A pressure regulator and pressure relief valve should always be used when pressure testing with nitrogen or CO2. The regulator makes it possible to safely control the pressure on the system. Never use oxygen or compressed air to pressurize a refrigeration system. Pure oxygen is a dangerous gas because of the increased risk of fire. Compressed air contains substances that should not be inside a refrigeration system, including oxygen and water. That'll make it pretty hard to pull a vacuum on that system later. Using R22 as a trace gas. Mix of nitrogen and R22, nitrogen mixed with 10% R22. That's how a lot of people pressurize a system to check for leaks. So mixtures of nitrogen and up to 10% R22 may be used to check for leaks using the R22 as trace gas. Trace gas meaning if you're using an electronic leak detector, if you only have nitrogen in the system, it's not going to pick up the leak because there's no refrigerant to detect. Your soap bubbles will, it'll blow a bubble if you find the leak with the nitrogen in there. But the purpose of the R22 being present is so that an electronic leak detector can actually pick up on the refrigerant escaping from the system. Mixing the R22 with nitrogen reduces the amount of refrigerant being released without being recovered. Mixtures of R22 and nitrogen may be released without being recovered, but nitrogen may not be put on top of existing R22. So basically, for the purposes of leak detection, that mixture is perfectly fine, but you would not, under any circumstances, run your system after that. If you have R22 in the system, you add nitrogen to increase the pressure and find the leak, you got to pull that all out at that point. Once you find the leak, and then make your repair and then move forward. But you do not want to run a system with nitrogen in it, and then also you don't want to leak check with all pure refrigerant, because that's just a huge waste of refrigerant. I mean, you're gonna need 150 psi. That's gonna be quite a bit of refrigerant just to find a leak and have to pull it all out. Leak testing with electronic sniffers. Electronic leak detectors have become the standard, good for general leak areas. Again, not for pinpointing, but it'll get you in the area, and then you pull out your soap bubble. Electronic leak detectors have largely replaced halide torches. These detectors have become the standard in leak detection since the era of the Clean Air Act and refrigeration conservation. These detectors are advertised to be able to detect leaks as small as 0.25 ounces per year. In reality, hypersensitivity can actually be a detriment to locating the exact location of a leak. It is a good tool for locating the general area of a leak, but soap bubbles work the best in pinpointing the leak. Corona discharge leak detectors. It's a bad time for tools with Corona in the name. I don't even want it. But yeah, so a Corona discharge leak detector. The first electronic leak detectors used Corona discharge technology. The Corona is a high voltage discharge that ionizes the gas it passes through. Anything that breaks that Corona barrier can set off the detector, including dust, moisture, refrigerant, or a good gust of wind. Corona discharge tips tend to become unreliable after as little as 20 hours of use. Wow. These tips are not expensive, and the detector can be restored to reliable operation by changing the tip. Most Corona discharge units continue to squeal for a long time after they are removed from the leak source, which makes locating exactly where the leak is more difficult. They can also give false readings when the wind blows on them, or when the tip is tapped against something. So yeah, not the greatest. Heated diode leak detectors. These detectors are a newer technology. These are the ones that I've used in the field. The main one that everybody's crazy about is the Bacharach. I don't think there's a graphic of it, but it works the same as this one, but it's supposed to be like, the top of the line. But it's an electronic leak detector, uses the same technology. So these detectors are a new technology that have proven to be sturdier and more reliable. Their tips last much longer uh, than the Corona discharge units, but they are more expensive to replace. Heated diode detectors use heated electrochemical sensors. When a CFC, HFC, or HCFC contacts with the hot surface, chlorine and fluorine atoms are separated from the molecule and ionized. This causes an electrical current flow in the sensor, indicating a leak. Infrared leak detectors. The newest handled electronic leak detectors use infrared sensors. They are not affected by wind, water, or oil, and the sensor's life is measured in years instead of hours. Refrigerant reflects infrared light. Refrigerant is drawn into the tip and travels between the infrared light source and the infrared light sensor. When refrigerant enters the tip, it reflects the infrared radiation and blocks the sensor from seeing it. Leak testing with dyes. Leak testing with dyes has been around for many years. The idea is that the escaping refrigerant will leave a visible trail. These dyes do not dye the refrigerant, they dye the refrigerant oil. So when you see those oil stains later on, like when you come back, people usually throw the dye in and go to their next job or something and come back. They're making them to where they work a little quicker, but when you come back, wherever there's a leak, you should see like little, you should be able to see it visually. Those dyes are also known to clog TXVs in some systems too. So might want to ask about that in the future before you buy one. Just make sure, you know, you get one that's maybe better than what they used to use. Proving the system is tight. Standing pressure test versus standing vacuum test. There are two methods of proving a system is free of leaks that do not involve checking for escaping gas. Standing pressure test, let me close that. Standing pressure test and standing vacuum test. A standing pressure test involves charging an empty system with inert gas, recording the pressure, and then checking back later to see if the pressure has dropped. This method is only valid when the system is charged with a gas that cannot possibly condense at the pressure and temperature found in the system, because a saturated mixture of liquid and gas refrigerant would change a pressure significantly as the ambient temperature changes. So basically use nitrogen. It's a common practice to wait after pulling a deep vacuum on a system to ensure that the pressure will not rise. A rise in pressure can be interpreted as air entering the system through a leak. Low pressure systems. Air is sucked through leaks. Leak testing low pressure chillers is different from leak testing high pressure systems. When a chiller leaks, air is sucked in through the leak. This forces the purge system to operate more to remove the air. So I think we talked about that yesterday and how those purge units work. Low pressure systems, raising the evaporator pressure. Technicians raise evaporator pressure above 0 psi to detect refrigeration leaks. This is done by either raising the water temperature in the chiller bundle or adding nitrogen. Circulating water is recommended though. So in summary, refrigeration systems should be leak tested before charging or whenever refrigerant needs to be added. Leak testing techniques include the following: soap bubble solution, halide torches, which work only on chlorinated refrigerants, ultrasonic leak detectors, which detect the sound of refrigerant escaping, electronic sniffers, which detect CFCs, HCFCs, and HFC refrigerants, dyes that make oil spots more visible, standing vacuum tests, and standing pressure tests. Significant leaks in systems that hold 50 pounds of refrigerant or more must be repaired. A significant leak is defined as an annual leak rate of 35% of the charge for commercial industrial refrigeration, or an annual leak rate of 15% of the charge for air conditioning systems and other applications. So that is all for Unit 27. Hope that was helpful. Again, read your books because that's where all the information is if you want to go even deeper than the PowerPoint. And also, Unit 27 review questions have been uploaded on FlexiQuiz. So get your work done. I'll check in with y'all later. All right.